Welcome back, student, to the fourth lecture of this final module about in-viscid flow, or we are going to derive. We were actually deriving the equations of velocity potential here. So to proceed forward, we are going to see we have already derived the dispersion relationship. So one thing you must remember, that the complex derivation you don't need to remember. The only thing that you need to remember are the end results. For example, the velocity potential phi and the dispersion relationship. Now whatever results we have obtained, we are going to apply in certain situations such as different water depth. All right. So this is a table, but first, without going into too much detail, first I would like to say there is something which we have said: deep waters, we have said intermediate waters, and we have shallow waters. So what are the definition of deep water? Deep water means that the depth of the water divided by the wavelength in which the wavelength of the wave, if it is greater than half, okay, that means it is deep water. If this ratio d by L is less than 1 by 20 or 0.05, okay, less than 0.05, that the depth of the water and to the ratio of the depth of the water to the wavelength of the wave, it is less than 1 by 20, that means we are in the shallow waters. And what the value in between 0.5 and 0.05, we call it intermediate waters. That is our definition. That is how we have defined what a deep water is and what a shallow water and what are the intermediate waters are. So if in case of deep water, if d by L is greater than half, then we will have 2 pi d by L will be greater than pi. What you do simply is 2 pi, just see d by L is greater than half. So 2 pi d by L will be greater than 2 pi into half. So this, for deep water, 2 by L will be greater than pi. Similarly, for intermediate waters, this value is going to be 2 pi d by L will be between pi by 10 and pi, and for below that in shallow waters it will be from 0 to pi by 10. Very simple to calculate yourself. So for this condition, when in 2 pi d by L is greater than pi, then tan h of 2 pi d by L can be approximated as 1. You can use your trigonometric calculators to find that. For shallow waters, if 2 pi d by L is 0 to pi by 10, we can approximate that is 2 pi d by L. So tan h will go away, whereas in case of intermediate it will remain the same, tan h 2 pi d by L. So these are three values of tan h 2 pi d by L that we get. All right. And this is the classification of ocean waves according to the water depth: deep water, intermediate water and shallow waters. Let us say the deep water condition. In case of deep water, equation 2.30. So what was equation number 2.30? So equation 2.30 was C square is equal to G by K tan H Kd. All right, now we go back to this. So C naught, because since tan H Kd is equal to 1, C naught will become under root G L naught by 2 pi. All right. And equation 2.31 was V C naught becomes G T by 2 pi, or L naught can also be written using this equation here, G by 2 pi T square. All right. Or we can also write L naught is G by 2 pi is 9.8 divided by 2 into 3.14 into T square, or L naught can be written as 1.56 T square. So in deep water, if we know the time period of the wave, wavelength can be simply derived as 1.56 times T square. A very important result. also the wave speed c naught gt by 2 pi 1.56 into t. You see how we have applied the findings into case of deep water. That is, when d by l is greater than half, tan h kd approaches unity and the wave characteristic are independent of water depth. One important thing to note is that here the term d does not appear in this equation, because the term that contained d was tan h, and this, the tan h term goes to 1 in case of deep water. Therefore, all the wave characteristics are independent of the water depth. This is an important result. So, L naught is in FPS. So, this is a different unit, but in SI units, which is the one that we are going to use, will be 1.56 times T square. This is the meter kilogram second unit, SI unit. So, if equation 2.33 and 2.34 are used to compute wave celerity for shallow water condition, so if we say that okay, we are going to use these same equation for shallow waters, we are going to get some errors of the order of 20 to 50%, alright, which is not good, because we need to get the correct value of the velocities in shallow water. Shallow water occurs near the coast, for example. Now, what are the shallow water conditions? Kd is equal to pi by 10, alright, that is what we said, 2 pi d by L, that is what we found out from the table. Therefore, C square can be written as GL by 2 pi tan h kd. Then if tan h kd can be written as kd is equal to 2 pi d by L, so this will become C square will become GL by 2 pi into 2 pi d by L, right. So, 2 pi gets cancelled and C square is equal to GD, same as what we have written here. Alright, so C is under root GD. So, in shallow waters, the wave speed will depend on nothing but only the water depth. In deep water, it was not dependent on the water depth, but in shallow water, the only thing on which the wave speed depends on is the water depth. If you recall, this is same equation as we got in open channel flow module. Remember, we got C is equal to under root GD by applying the principles of continuity, momentum and energy balance. Okay, so in shallow waters, wave speed is under root GD, where D is the depth of the water. So, as I said, this relationship shows that when a wave travels in shallow water, wave celerity depends only on the water depth. Now, relationship between D by L and D by L naught. If you divide equation 2.31 by equation 2.33 and equation 2.32 by equation 2.34, we can simply get, so 2.31 and 2.32 are the equations which are for general form. 33 and 34 was those of deep water. So, if we divide those, we can get C by C naught is equal to L by L naught is equal to tan h kd. Alright, you can try this on your own. Now, if we multiply both side by D by L, we can get D by L naught is equal to D by L tan h kd. Alright. Now, the relationship between D by L naught and D by L and D by L naught is given in wave tables also. So, this is something, if you want to calculate, there is something called wave tables, which I will not show you in this course, but if you need to solve, you can always use trial and error method for solution of the dispersion relationship. But most of the question that you will be getting will be in your assignments will be based either on deep water or very simple, that you can use the equations like the dispersion relationship or the velocity potential. Where a lot of iterations and intermediate water determination would be required, I will not be giving those type of problems for you to solve, because the idea here is that you understand the basics of wave mechanics, and therefore if I give you more questions about intermediate waters, it will only complicate the calculations. Therefore, the use of wave tables will not be is not encouraged. However, I can try to give you questions in your assignment, one or two, which will show exactly how to use the iterative formula, iterative procedure. All right, and I can also post some couple of questions in the forum where you are going to use those iteration method for solving the wave amplitude, or sorry the intermediate water depth properties. All right. So this is the curve which denotes the relationship between d by L and d by L naught. Okay, so the right hand side, this shows d by L naught. Okay, and so see. All right, proceeding forward. Now we have found out the velocity potential, we have found out the dispersion relationship. Now it's time to find out the local fluid particle velocities and acceleration under progressive waves. These, so in the evaluation of, I mean, first, more importantly, why do we need to find out these velocities and acceleration? Because in evaluation of wave forces on offshore structures, it is desirable to know the fluid particle kinematics, that is velocity and acceleration. We know that phi is equal to Ag by sigma, this we have derived this equation. All right. The horizontal particle velocity or the orbital velocity u is given by del minus del phi del x. All right, definition of velocity potential. So we get Ag by sigma k into cos h k d plus z by cos h k d into sin k x minus sigma t, whereas all right. So if we substitute the relationship c square is equal to g by k tan h k d and small a as h by 2, because this is wave height and this is wave celerity, we get u is equal to h by 2 sigma c square k square divided by cos h k d plus z by sin h k d into sin k x minus sigma t. It is enough if you remember the velocity potential equation, because that you can differentiate and try to find out the velocities. Maximum you will be given, find out the velocities at z is equal to 0 or at the water depth where z is equal to minus d, because those are pretty simple to calculate. Or maximum velocity, when you talk about maximum velocity, this will be assumed to be 1 for the maximum velocity case. All right. So just doing manipulation, writing in terms of L and T, this equation you can remember but not mandatory, since you will definitely remember the velocity potential equation, and therefore you can derive this u even for your assignments and exams. So it's pi h by t cos h k d plus z divided by sin h k d into sin k x minus sigma t. This is the periodic term. Periodic term in x and t, sin k x minus sigma t. All right. And similarly, we can find the vertical fluid velocity is given by minus del phi del z. Okay, and therefore we can similar substitutions will give us minus pi h by t sin h k d plus z divided by sin h k d. Again, you don't have to remember this, but if you do, it's no harm, because more importantly it is the velocity potential that you must be remembering. All right. So w can be written as minus pi h by t sin h k into d plus z divided by sin h k d into cos k x minus sigma t. All right. So the equation expresses the velocity components with the wave at any depth z. At a given z, all the velocities are seen to be harmonic in x and t as shown in figure. Let's if we plot those, it's harmonic, but with different z, this is the variation which we are getting if we plot those velocities. All right. So, figure 2.4a, this figure, it shows the horizontal velocity component are the hyperbolic functions of the depth. You see, sin hk d plus z, okay, hyperbolic functions of d plus z, and same with u also. You see, one is u is in cos hk and this is in sin hk, the u and w. Okay. We say at any phase angle theta, phase angle is kx minus sigma t. The hyperbolic functions of z, that is cos h and sin h, cause an exponential decay of u and w with the distance down from the sea surface. This is indicated schematically in this figure. Okay. These are just the findings. You should not put a lot of effort and concentration in finding these values, but this is pretty true, right, that there is an exponential decay of u and w with the distance down from the surface. All right, variation of maximum u and w, because cos if we take a phase angle fixed phi, so whatever that is, that does not really matter, because it will be the same for different z. The periodic will be the same, because cos theta or sin theta will remain the same. So, here the phase angle assumed to be 0, theta is equal to 0, u is equal to 0 and w is negative. All right. Here theta is pi by 2 and u is assumed, u is positive and w is 0 at the top. Here theta is equal to pi, u is 0, but w is positive. At 3 pi by 2, u is negative and w is equal to 0. If you put in the velocity potential and u and w equation, different thetas, different values you are going to get, and the sign will be determined from there. So, this is just a summary of those results obtained from this equation. More importantly, this is theta is equal to 0 starting from here. This is theta is equal to pi by 2, this is theta is equal to pi, this is theta is equal to 3 pi by 2 and this is theta is equal to 2 pi. So, phase is changing by pi by 2 from this point to this point to this point to this point and to this point finally. So, this is variation of u and w with phase. Now, we have talked about the velocity. Similar way we should talk about acceleration as well. So, ax is del u del t, all right, because u we have already obtained in terms of h, t and cos h. So, we simply differentiate once more. So, sin becomes cos here with a negative sign, and similarly a w will become cos, will become sin with a negative sign. Okay. Sorry, here it was sin, so it becomes cos and there was already a negative sign, and in AW this cos was there and it becomes sin after the differentiation with a negative sign. All right. So, this expression for fluid particle kinematics reported above is for water surface elevation being a sine curve. So, we have started with a velocity potential where our time variation was sin kx minus sigma t. So, similarly, if we assume a cosine curve, the velocities, the phi can be derived as sin kx minus sigma t, correct? So, in this case eta will be a cos kx minus sigma t, the u's will change, u and ax and w and aw, all right. So, if we assume a different velocity potential, you remember we had two velocity potentials. So, we started doing all the calculation with the first velocity potential, but instead of the first, if we started with the second, we will obtain this set of wave kinematic wave kinematic parameters. All right. All right. So, we have studied the velocity potential, we have found out the velocities under the progressive wave, we have found out the acceleration. Now, importantly, we have to find out water particle displacement. Water particle displacement is nothing but integral u times dt and w times dt in x and z direction respectively. So, the expression of individual horizontal and vertical particle displacement is integral u dt. U we already know in terms of h before. So, the final results comes out to be h by 2 cos h k d plus z divided by sin h k d into cos k x minus sigma t. Similarly, the vertical displacement delta z is given by h by 2 sin h k d plus z into sin h k d into sin k x minus sigma t. These are the periodic terms. Okay. So, once you derive the velocity potential, everything can be found out. Now, if we say delta x is equal to d cos k x sigma t, k x minus sigma t, and we say d is h by 2 cos h k d plus z divided by sin h k d. And similarly, we assume delta z is b sin k x minus sigma t, where b is a different quantity called h by 2 sin h k d plus z divided by sin h. Therefore, we can write cos squared k x minus sigma t is delta x by d whole square. All right. Let us go back. So, what we have said is this is d and this is b. All right. So, if we take d down, so it will become delta x by d is equal to cos k x minus sigma t, and if we take b down here, it becomes delta z by d is equal to sin k x minus sigma t. All right. So, sin square theta plus cos square theta is equal to 1. Therefore, this is what we have used. So, what we write is delta x by d whole square plus delta z by b whole square is equal to 1. This is in general what type of equation if d is not equal to b? Elliptical. So, this is an equation of an ellipse showing that water particle moves in an elliptical orbit. So, we have proved particle moves in an elliptical orbit. All right. Here d is the semi major axis, like the horizontal measure of the particle displacement, and b is the semi minor axis, that is the vertical measure of the particle displacement. Okay, so the particle displacement, this is an important equation. Okay. Now, we analyze this displacement in shallow water. So, what happens in shallow water for d by L less than 1 by 20 or 0.05, we have used cos h k d plus z and sin h k d plus z. So, sin h k d plus z goes to k d plus z and sin h k d goes to k d. All right. Hence, d will be what? If we, as you remember, d was this equation, d was h by 2 cos h k d plus z and sin h k d. In shallow water, this becomes k d plus z divided by k d. All right. So, this capital D becomes h by 2 into 1 by k d. All right. and B becomes h by 2 k d plus z by k d. Alright. Hence, the water particle in shallow water moves in an elliptical orbit in shallow and intermediate waters with the equation of the form, which just simply substituted in shallow and intermediate waters with this d and b. But in deep water for the case d by L greater than half, d becomes h by 2 e to the power k d plus z plus e to the power minus k d plus z divided by e to the power k d minus e to the power minus k d. As d is very large, e to the power minus k d plus z and e to the power minus k d will be very small, correct, because this it's deep, na. So, if with minus sign they will be very small compared to e to the power k d plus z. So, this can be taken away, alright, and therefore, we can write h by 2 e to the power k d plus z divided by e to the power k d and simply h by 2 e to the power k z. Okay. This is important. Similarly, if we do the same process with B, we will again get h by 2 e to the power k z, because in deep water that is going to happen again. Therefore, you see both B and D are same. So, in an ellipse, if both the major and minor axes are same, it is nothing but a circle. Therefore, the particles move in circular orbits in deep water, since d is equal to b, with the equation of the form delta x divided by h by 2 e to the power k z plus delta z h by 2 e to the power k z whole square is equal to 1. All right. So, see, these things are very important. These are the type of questions which you can expect. What type of orbit in deep water? Then you have to mark the correct one as a circular orbit, elliptical orbit. Okay. This shows that for deep water condition, the water particle trajectories are circular. So, you see, this is the representation, the schematic representation of fluid particle trajectories. The amplitude of the water particle displacement, first of all, it decreases exponentially along the water depth. Okay, the water particle displacement becomes small relative to the wave height at a depth equal to 1/2 the wavelength below the still water level, that is the deep water. The variation of the water particle displacements under the depth condition is illustrated in this. All right. So, there is one last thing before the end of this lecture. I have included in the slide, but does not have any significance for this particular course. You see the dispersion relationship, I said there are two solutions, one is either using the wave tables and the second is trial and error, but some scientists like Hunt, he came up with the direct solution for Kd. He said Kd square is equal to y square plus y divided by 1 plus n goes from 1 to 6 dn yn, and this final equation can be used in MATLAB or Excel to determine for different y's. So, if you can put it on a computer code using MATLAB or Excel, there is no need for iteration or any other method. So, this is just for information purpose. You do not need to remember. Maybe the name, the if somebody is interested in doing further research or going for a master's program or something related to research, they can use this equation as such. So, with this Actually, this equation is accurate for 0.1% for y varying from 0 to infinity. Okay. So, I think this is a fine point to stop, and in the next lecture we will conclude this module of in viscid flow, that is wave mechanics, and we start with the pressure distribution under progressive waves from the next lecture and finish this module, and this will also be the end of the course, but I will talk about it in the last lecture of this course called hydraulic engineering. Thank you so much for listening. See you in the next lecture.